So another a core set of concepts with QEC is stabilizers. So stabilizers are operations which they don't affect the logical state, so they act almost like an identity operation, but only for the class of states that you're using to encode your qubits, your logical state. You can have more than one stabilizer. You can have actually a group of stabilizers, and these are all operations. They must commute with each other. So when two matrices commute, the order of multiplication doesn't matter. So AB equals BA, or equivalently, AB minus BA equals 0. And here's an important point. The stabilizers are chosen not only to leave the logical state invariant, but they anti-commute with the errors. So we design we choose our stabilizers such that the expected errors that we will see in the system will anti-commute with our stabilizers. And so the takeaway here is that our stabilizer operations are used to detect errors. So I have a simple example here. This is a Bell state, entangled state, and we can see two stabilizers here, a Z gate, Z on the first qubit, Z0, and then Z1. If we apply this operation to the state will be unchanged. And similarly, if we apply bit flips to both qubits, the state will also be unchanged. So these are stabilizers. Now you might ask, well, which one should we use since they both stabilize the state? Well, it will depend on which type of error you're expecting. So if you are expecting bit flip errors, which correspond to X-gate operations, then you want the stabilizer that anti-commutes with the X, so you would use the Z stabilizers. And conversely, if you're expecting phase flip errors or Z-gate type errors operating on your qubits, you would choose X stabilizers. So one more point here, if you were actually trying to stabilize this state and it was distributed across two nodes, you would have to execute these gates in a synchronized way in order for that to properly stabilize the state.